Hello and welcome to today's video. We're going to do some proof by contradiction. We're going to do two and also provide a little introduction. So proof by contradiction, what you do is you assume the logical negation of the result you want to prove, and then you reach some contradiction. So you assume the opposite, and then for some reason something's going to happen that's going to make it just not true, and that's the contradiction that you're looking for, and then you're done with the proof. And it's really your third option. So you would prefer to do direct proof, then you would prefer to do proof by contraposition, so contrapositive, and then you would want to consider proof by contradiction. It's not like the most common, and you use it to prove the impossibility of something usually, so you assume it's possible and then reach some contradiction. And the most popular proof by contradiction that I've seen is definitely the proof of rational numbers. So if I want to show that the square root of 2 is irrational, this is one that I can't prove directly. I also can't do it by contrapositive, so I'm left with proving by contradiction. So how do we do it? Well, and just so you know, this one is pretty challenging, so if you don't get it right away, that's okay. So what we do is we assume the opposite, so we assume square root of 2 is rational, right? Because that's what contradiction is. Okay, so that means that square root of 2 equals p divided by q, where p and q are both integers, and we're assuming it's the most simple rational number that we can get, and p and q share no common factors. No common factors, because as you know, a rational number is any number that can be written as a fraction. So that means that for every fraction, there's obviously a simplified form where you take out all the common divisors and things like that, and you get its simplest form. Well, we're assuming p and q that we've written here, we're assuming that is the simplest form. So they share nothing in common. All right, so now we're going to square both sides. So I'm going to get 2 equals p squared divided by q squared. I'm going to move this around. I'm going to get 2q squared equals p squared. So now is when it gets really interesting. So what can I tell you about p squared right now? Well, I can say p squared is even. And why can I say p squared is even? Well, because I have 2 times some integer equals p squared, so p squared has to be even, just by the definition of even, where it's 2 times some integer. All right, so p squared is even. Well, that actually implies that p is even. Because if a square has a factor, the square root has to have the same factor. So what I'm saying is p squared is divisible by 2. So 2 divides p squared. That implies that 2 divides p. So that's important to know just in general. If 2 divides p squared, if any number divides the square of something, then that same number divides the square root of that same thing. Okay, so I've assumed p is even. Well, now if p is even, I can say p equals 2k, right? Nothing wrong with that. And now I'm going to go back to the drawing board here and say, well, 2q squared equals instead of p, I'm going to say 2k squared. Then I'm going to get 2q squared equals 4k squared. Okay, now I'm going to divide both sides by 2. I'll get q squared equals 2k squared. And this is the answer right here. It's right on the page right now that there's a contradiction. But let's go step by step. So I just solved all of this. That was okay. And now what have I proven here? Well, I've shown that q squared is even, right? Because I have 2 times some number k squared equals q squared. So q squared is even. And like we said again, that implies that q is even. Now the light bulb should be going off with this sentence and this sentence. If q is even and p is even, well, that means that they share the factor of 2, right? So p and q both can be divided by 2, are both divided by 2, both divisible by 2, because that's the definition of even. And that means that they share a common factor, which is a contradiction. So you can't be divisible by 2 and share no common factors. Can't be divisible by 2 and share no common factors. Can't both be divisible by 2. And that means that we've reached a contradiction. They cannot both be divisible by 2 and share no common factors, because they obviously share the common factor of 2. And so that means we've reached a contradiction. No common factors. So we reached a contradiction. This can't be true. The fact that the square root of 2 is rational can't be true, which shows that it must be irrational. So can't both divide by 2 and share no common factors. So hopefully that makes sense. This is an important proof. You see all kinds of variations of this. They'll ask you square root of 3 and things like that. So just make sure you know that one. And now let's see another example that you may consider using proof by contradiction. Hopefully you see this and you think of another way to do it that we've talked about, and there's a much easier way to do it than the contradiction that we're going to show here. So the contradiction shows that, well, I'm going to assume that the opposite is true. So I'm assuming n is even, because that's the opposite of odd, so not odd is even. So I'm assuming n is even. I'm still trying to arrive at the same conclusion that 3n plus 2 is an odd integer. And if there, for some reason I can't arrive at that, then I have the proof by contradiction done. So assume n is even. N equals 2k, where k is an element of z. That means that 3n plus 2 equals 3 times 2k plus 2, which equals 6k plus 2. And how can I make this look like just 2k? I can just rewrite it as factor out of 2 and get 3k plus 1. And 3k plus 1, I'm going to set that equal to L. And I'll get 3n plus 2 equals 2 times L. And where L is an element of z. So L is an integer, of course. And that means that 3n plus 2 is even. Well, that means that 3n plus 2 is even and odd, because I was trying to show that it was odd. So 3n plus 2 is even and odd. That's a contradiction. And odd. That's the contradiction that I've arrived at here, because what we do with contradiction, we kind of assume the result is still, we assume the first part's still true. So we're assuming that 3n plus 2 is odd, but n is actually even. So we're just trying to show that, can I arrive at that conclusion, or am I going to reach a contradiction? And here you do reach a contradiction. So that's the end of the proof. We've somehow shown that when n is even, when it's not odd, you can't get to that result. So that's a valid reason. But if you notice, we actually basically just did contraposition. So that's definitely the way you would want to do this one. So contraposition, we literally almost did it right here. There's just a slight difference here. We assume not q, and then we just show that it's even, and that's enough. We could end this step here. Instead of showing that, well, we assuming that's odd and then it's even and all that, we could end it a step early. So hopefully that makes sense, that you should use contraposition here. That's what I was saying, that contradiction really should be your third option, not your first or second. So hopefully this makes sense. The important thing here is that you know how to do this one, and that you realize kind of the uses of contradiction and when not to use it. Thanks for watching, and let me know if you have any questions. Have a good one.